First and last speaker today is Akimova. She will speak on classification of prime genus 1 virtual nodes of low complexity.
Okay. Remember that classical node K is just an arbitrary closed simple curve which is situated in a three-dimensional sphere. As a rule, such nodes are represented by their projections in the plane. Now it is example. It is projection on the trefoil. One can easily get a node diagram from projection by choosing the type of each crossing. That is, so one of the trefoil diagram looks like this one. The table of first table of classical node was composed by Tricard at the end of the 19th century. After him, we needed to after him, tables of classical nodes were composed by Olsen and Vanatan. Today, all classical nodes having diagrams with at most 16 crossings are tabulated. They are more than 100.5 million. It was made by Weeks and Christmas Way. Okay. Node theory also interested in nodes which are situated in the other three-dimensional manifolds. For example, today there are some tables of global nodes. They are planes which are situated in a projection sphere, having diagrams with at most 6 crossings. I have forgotten to say that by crossing we understand the point of the plane in which 2 points of node are situated. Example this one. The complexity of projection is the number of crossings in it. For example, complexity of this projection is 3. So when I say in the projection sphere, all links having diagrams with at most 6 crossings are tabulated. Yes. Another table is table of nodes in solid torus. Also having diagrams with at most 6 crossings. And the last one table is a table of virtual nodes. Virtual nodes having diagram with at most 4 classical crossings. Okay. We in knots which are situated in a thickened torus. Remember what a thickened torus is. Thickened torus is a direct product of the torus and an integral. So T is a torus and I is an integral. Remember that torus is just a direct product of two one-dimensional circles. So, knots in a thickened torus is also just an arbitrary simple closed curves, which are situated in a thickened torus. Such knots, as a classical ones, as a rule, represented by the diagrams or projections. Difference is the following. We project not in the plane but in the surface. In our case it is by torus. So we will draw knots by where diagrams in a torus. An example is here. Also, we will use following representation. Let torus be a square with an identified opposite sides. Then knot diagram in torus is just a set of arcs in with square. As you can see, the number of lengths of arcs on the opposite sides should be equal. So in this case it is 1 and 1. We need it to for that factor where the curve should be closed. Yes, so two projections in torus, G and G prime, is called equivalent if there is a homeomorphism of a pair which takes one projection to another one. The definition of equivalence of diagram is the same. And in addition, we admit to change all types of crossing points to an opposite one. So all such became such one. Tables of knots contains not all knots, but some knots from which which all other knots can be composed. We call them prime with stronger definition will be get now. Okay. First of all, we need to understand what is a composite knot. In a thickened torus. We say that knot K in thickened torus is a composite if one of the following is true. First one is following. I show an example. So we have a torus and some diagram in it. So why we say that with knot is why we say that with knot is composite? That is the following. Where there is a disk on torus which intersect our diagram in exactly 2 points, and inside of this disk are situated the part of non-trivial part of the diagram. In other words, we just take knot diagram on torus and tie some local knot in it. And the second reason why we say that knot is composite is the following. I also want to show an example. So it is what we need from this picture. On torus, in torus, there are 2 non-trivial curves which are parallel, and which one? And they are following. They intersect knot diagram at 1 point here and here. Why we say that with knot diagram is composite? Because one can cut by with non-trivial curves, and after that glue together. So we get two exemplars of thickened canals, and we can glue the opposite sides together so as to get a thickened torus here and here. So we say that this node is composed from this node and this one. Okay, such nodes we will call composite. Now definition. We say that knot K it means destabilizations if there exists diagram of K such that one can choose non-trivial curve vectors which do not intersect with diagram. For example, this one cut along with non-trivial curve and glue two discs to the закрыть края посредством диска.
Glue together. Attach discs.
Attach discs. Okay. So we are not interested in such diagrams because they are correspond to nodes which are situated not just in thickened but also in thickened channels, and if we want a trivial example, this diagram is situated not only in thickened but just in a thickened two-dimensional sphere. It is just classical node and we do not interested in it because such nodes are composite. So, nodes which are not composite and admits no destabilizations we call prime. So we want to get such table which contains only prime nodes. Because nodes which are not prime are tabulated earlier or can be get from prime nodes. So now it is agreed how we can compose a table of such prime vectors. First of all, we need to enumerate all abstract regular waves of degree 4. After that, we consider all possible ways to embed such graphs in torus so as to get projections of nodes. Now, when we have a list of projections, we associate each projection with a set of corresponding diagrams. And the last step is the following. We prove that all diagrams are non-equivalent I should say that we need only graphs of degree 4 and without loops. Why without loops? The answer is the following. If loop of the graph, for example, this one, if a loop of the graph corresponds to trivial loop on a torus, we can admit the first reduced remove and remove with loop, so with such diagram will not be minimal. If such loop correspond to non-trivial loop, then it is easy to see that such diagram admits the stabilization. So we can choose such non-trivial curve, cut torus by it, and see that such node contains significant nulls. So there are 11 abstract trivial graph of degree 4 without loops. We should to consider all possible ways to embed such graphs in a torus so as to get not projections.
But the heuristic of only 10, yes?
Excuse me?
The heuristic of 10.
Okay, from 8 to 3. From 8 to 3.
Oh,
So, I want to say some ideas. The first one works for graphs which looks like this one. So, it is all graphs which satisfy with condition. As you can see, such graphs are just close. Close chain of 2 or 3 circles. Which circle can be trivial on torus. So, or non-trivial. And so on. Hello. Suppose that common point of 2 circles are transverse. On torus, it can be only in the case when these circles are non-trivial and they are parallel and ventricule of a torus. We need some definitions. If a common point of two edges is non-transverse, we can remove it the following way. We can change it by arc which we call A. So from 2 points and 3 points, only 1 point can be transverse, and other ones should be non-transverse. So 1 point is transverse, so we have a drawer for this case, and other circles for this one is situated here. It is non-transverse points. Or in this case, so we have changed the arc to a non-transverse point. How would
Значит, во сколько? Ну, 20, 25.
20.
А? Больше?
7 минут.
7 минут у меня осталось?
Ну, 8.
Что, серьезно?
Ну, да, минут 15 есть. Начали позже, да, говорят.
Following idea works for grass with 4 or 5 vertices. It is the following one. If suppose that our projection contains face with 2 angles, which we will call 2 bianco face. Then one can change this bianco face by also by arc. So to get all knot projections having such element having 2 bianco face, it is enough to consider all knot projection having. So if our projection contains n crossings, it is enough to consider all projections having n minus 2 crossings and consider all possible ways to connect two edges of projections together by this arc, and to change this arc by the angle face. How it is work? Let us consider some knot projection doors having just 2 crossings. Let us choose some arc, and change with arc by triangle face. So the other part of projection is the same. So we get such projection. We change with arc by triangle face. Easy.
Что такое?
Большинство.
Majority.
Не, большинство.
А?
The main part of graph of this graph contains double edges, for example. So if with double edges corresponds to triangle face, then to get all such projections, we can get all such projections by using this idea. So first theorem is the following. There exists exactly 47 different prime projection because you can see the list of these projections on the first page on the table. I should say why these projections are different. To show that all projections in our list are different, we do the following. Let us calculate all angles in each space. For example, here it is 2, 2, 3, 3, and the last one is 10. We do the same for this projection. You can see 2, 2, 3, 3, and the last one is also 10. Every projection in our list contains such string. Also, it includes a type of the corresponding graph. In both situations, it is J. But we say that these projections are different. Why? Because in the first case, two triangle faces contain common edge, and here they contain only a common point. As a rule, such strings are enough to prove that projections are different. So now we have a list of projections, and next step is to compose a list of diagrams. To this end, we should just do associate each crossing point with one of following types. So if we have a projection G having n crossing points, there are 2 power n different diagrams which corresponds to it. It is a very big number, but we need to get only prime and not non-equivalent diagrams. So we can use some ideas which allows to do not consider some trivial cases. For example, first one is the following. If first idea is the following. If we change all types of crossings to the opposite one, we get a diagram which is equivalent to the first one. So the type of one crossing point we can choose and we can fix. And the second idea, which is more interesting, is the following. Suppose that projection contains one of the following fragments. So this one, this one, or this one. The claim of that all such fragments, it means just 2 possible realizations in diagram. It is a following. They should be alternate. Example is shown. They should be alternate. Why it is so? Because if we choose another way, for example, this one can see that this part of string can be moved so as to get such fragment. So diagram which contains such fragment is not minimal, because we can simplify it so as to get a diagram having n-1 crossings.
раз сформулируйте основное и как там различают основные вещи. Потому что мучить этим проекциями ничего такое. Проекции все разные, руками делали. Теперь давайте узнаем.
Вот мы получили список. Now we have a list of diagrams, notes in doors, of notes and doors. And we should to show that all of them are different. We do it by using following invariant. So minus I power minus 3 omega so it is normalized Kaufman bracket for knots in a thickened torus. The definition of it is rather long. Длинное определение.
А?
Определение длинное.
Не понял, определение чего?
Ну вот это недолго сказать. Я уже его закончила.
Да ничего, скажите, что такое и, что такое А. А было, а X не было.
Let us consider some node diagram. It contains two crosses, so first of all we associate each angle with a mark A or B.
Да?
Each crossing
Тут лучше нетривиальных. А?
we can resolve by the rule A
Ну, делайте. Почему?
or by the rule B. So,
Извините, мне правильно сказали, пишется тоже как и лучше. Если нетривиальных лучше, поэтому очень не лучше.
so for this diagram, we first of all we resolve by AA, and the last one.
Ну, ладно, понятно.
So you can see that in this situation we have one trivial circle in torus and one non-trivial circle in torus. And in this situation we have only one non-trivial circle in each one. So we should correspond to each situation for example for this one the power of the number of trivial circle in it is 1 times x in the power of the number of non-trivial circle in this one in the power of the number of marks A, it is 2 minus the number of marks B, it is 0. So the first situation involves times x. Following two situations involve x times a in the power 1 minus 1, it is just x. And the last situation involve x times a in the power 0 minus 2. After that, we should
Что сейчас рассказывать, я не хочу.
складывать их надо.
Зачем?
Ну, я рассказываю, как нам считать.
Ну, а нельзя сказать, что просто то же самое, что было, только нетривиальное, считаемое в иксах. Ну, на каком-то примере это невозможно понять, что делать.
Ты спасал.
Да?
So to each situation we correspond to some.
Алена, как определяется полином Кауфмана, рассказывать не надо, все знают. А я не знаю, что это самое. Надо сказать, что вычислили полином вообще Кауфмана, обобщенное с третьей переменной, и получили разные ответы, все.
Вы закончили или нет?
Нет, пусть она скажет.
All diagrams in our table have different normalized Kaufman rates.
А сколько всего тогда?
Where exists exactly 19.
Вы раздали таблицу, да, есть?
Да. 19
А,
different prime nodes having diagrams with at most 5 persons.
Скажите, что закончилось. Ну ладно. So the talk is finished. Let's some questions, please. Вы там еще have you tried to classify knots with 6 crossings?
Of course.
How many knots with 6 crossings you have?
I have tabulate nodes having diagrams which correspond to the octave front. The number of such diagrams is 54.
Okay.
So
Okay, if there are no other questions, let's have a speaker.